In this video lecture, I'd like to talk about the ratio and the root tests. These are two more tests for the convergence or divergence of infinite series. So I begin with the ratio test. So the ratio test, if we're looking at an infinite series of this form where none of the terms are zero, they're all non-zero terms. So the ratio test says that the series converges if the limit of the ratio of one term to the next term is less than 1 in absolute value, then it converges absolutely. All right, so this could apply to a alternating series as well. And then it would diverge if that limit is greater than 1, including if it blows up to infinity. And then it's inconclusive, unfortunately. This is one downside to this test, is inconclusive if the limit equals 1. So there's a couple of things I want to say about this by way of contrast with other things that we've seen already about tests for convergence or divergence. First, this is the big temptation, right? Just to look at the sequence of the terms of the series and say if that goes to 0, then they must be getting really small, and therefore the series will converge. What we know, though, that implies nothing about the infinite series. And remember, we have the example of 1 over n. All right, we know that this diverges even though the sequence 1 over n, as n goes to infinity, goes to 0, the series diverges. All right, so that's our classic counterexample to show that if the terms of the series go to 0, that doesn't say anything about the sum of the series. On the other hand, we do know that if they don't go to 0, then it does diverge. But if it does go to 0, we don't know. It could diverge, it could converge. So I will say this, though. There is some intuition here that the ratio test draws on. The intuition here is that, well, the terms of the series should get infinitely small in going to 0 in order for the series to converge. The question is, how fast would they have to go to 0? Obviously, 1 over n isn't fast enough. This test gives us an answer to that question. It says if I take the ratio of one term, of the nth term with the n plus first term, right? So of consecutive terms in the series, and as I go to infinity, that ratio is less than 1, then that's fast enough to guarantee that the infinite series will converge. The other thing I'd like to point out about this test is that these are terms of the same series. All right, and I want to contrast that with the limit comparison test, where we have a given series, and this is the one that maybe we want to show. We want to show whether or not that converges or diverges. Then we have to get a comparison series, which we might call the B sub n's. And we take the limit of the terms of the one series with the terms of the other, and if that goes to a finite limit, less than infinity, then they converge or diverge together. But I just want to contrast what we're doing here is we were looking at the ratio of the terms of two different series. Here, we are looking at the ratio of terms of the same series. So we're looking at consecutive terms and how fast do they shrink to 0. So that's what the ratio test does for us, and that's how it differs from the limit comparison test. So let's look at an example. I think that's probably the easiest way to understand how this works. So let's look at the series n equals 1 to infinity of 2 to the n over n factorial. And the question that we're going to try to answer here is which one grows faster? And if n factorial grows faster than 2 to the n, does it grow fast enough to guarantee that the series will converge? So we begin by just taking the limit as n goes to infinity of the absolute value, and now we look at the nth plus first term here. So I just replace n with n plus 1. So 2n plus 1 over n plus 1 factorial over the nth term, which is just the one that's given here, 2 to the n over n factorial. And this is all an absolute value, although I'm going to drop the absolute value because 2 to the n and n factorial will always be positive, so the absolute value is unnecessary here. So what I'm going to do is now just rewrite this and multiply by the reciprocal. So I end up with 2 to the n plus 1 times n factorial over n plus 1 factorial times 2 to the n. And the next trick is to rewrite these the 2 to the n plus 1. 2 to the n plus 1 is 2 times 2 to the n, right? Because if the bases are the same, we just add the exponents, and then that's times n factorial. And of course, we know n plus 1 factorial is n plus 1 times n factorial. So we would just keep going all the way down. That's exactly what n plus 1 factorial is. And then just have my 2 to the n here. And the reason we would rewrite these becomes obvious now because we get some cancellation. 2 times 2 to the n, so the 2 to the n's cancel. N factorial cancels with n factorial, and now we're taking the limit as n goes to infinity of 2 over n plus 1, which we know equals 0. Since 2 is constant, n grows without bound. This implies that the series converges. It implies that it converges absolutely, but since this isn't an alternating series, converging and converging absolutely are the same thing. Okay, let's look at a different example. Let's look at the series n equals 1 to infinity of n to the nth power over n factorial. And again, the question is which one grows faster, and if n factorial grows faster, does it grow fast enough to guarantee that this converges? So once again, we take the limit as n goes to infinity, absolute value, and everywhere we see an n, we'll replace it with n plus 1. n plus 1 to the n plus 1 over n plus 1 factorial over, so that's the n plus first term, the ratio of that with the nth term, which is already given there, n to the n over n factorial. Again, absolute value is unnecessary here since n to the n and n factorial will always be positive, so I'm going to just rewrite this as n plus 1 to the n plus 1 over n plus 1. I'm just going to go ahead and rewrite it as n factorial because we're going to have the same thing we had going on up here. So n plus 1 times n factorial, and then we multiply by the reciprocal here, so I've got n factorial over n to the n. So now the n factorial cancels with n factorial. Notice now that I have n plus 1 to the n plus 1 over n plus 1. So if I divide out one of these n plus 1s, I'm just left with n. So now I have n plus 1 to the nth power, kind of getting off the edge there, alright, over n to the n. I can rewrite that as n plus 1 over n to the nth power, which can further be rewritten. If I take n over n, I get 1, and then 1 over n, so I have 1 plus 1 over n to the nth power. And we're taking the limit of that as n goes to infinity. Now this is a sequence that's worth knowing. We've actually already looked at it. We could use L'Hopital's rule. We could say the limit as x goes to infinity of 1 plus 1 over x to the x. Now the way we approached this, because we had an exponent here, was to take the natural log, right? So we took the natural log, 1 plus 1 over x to the x power. Introducing natural log means that we can bring this out front. And whatever limit we end up with, since we've introduced natural log, whatever limit we end up with here, we make the power of e. Alright, so I end up with x times ln of 1 plus 1 over x. I take the limit as x goes to infinity. I get infinity times, now as x goes to infinity, 1 over x goes to 0. So this becomes the limit of, the natural log of 1, which is 0. So if I rewrite this, limit as x goes to infinity of natural log of 1 plus 1 over x over 1 over x. Now I've got 0 over 0, which is an indeterminate form. I'm running out of room, and well, I'm running out of space too. Let me just say you can apply L'Hopital's rule here, and you would get that the limit of that equals 1. And since we said that we've introduced the natural log, whatever this limit is, we need to make the power of e, then this limit equals e to the first power, which is e. Alright, so that means this limit equals e. Again, this is this one of 1 plus 1 over n all to the nth power as n goes to infinity. The fact that that equals e is worth knowing, but we can always go back and show it using L'Hopital's rule. So, what does this say about my series? Well, e is greater than 1, so it shows that that series diverges. All right. Now, I do want to show, I said before, we said that this is, that the ratio test is inconclusive. So I just want to show two quick examples of that. Let's take a look at a couple series that we already know what happens. So if we look at the series n equals 1 to infinity of 1 over n, we know that diverges. That's the harmonic series. That's one that we can show using the integral test that it diverges. But if we were to apply the ratio test, we would be looking at the limit as n goes to infinity of 1 over n plus 1 over 1 over n in absolute value. Again, absolute value is unnecessary in this case, so I'm taking a look at the limit as n goes to infinity, multiplied by the reciprocal. I've got n over n plus 1, and that equals 1. Yet we know that this series diverges. Let's take a look at another one that we know, 1 over n squared. All right, both of these, we can look at them as p-series tests. We know p-series only converge when p is greater than 1. Here it's equal to 1, so it diverges. Here it's greater than 1, so it converges. But once again, limit as n goes to infinity of 1 over n plus 1 squared over 1 over n squared. This is the limit as n goes to infinity of n squared over, and if we expand that out, we get n squared plus 2n plus 1. All right, well, in general, when I have something like this, you could use L'Hopital's rule if you want, but I can just look at the ratio of the leading coefficients, right? Because for large values of n, these other ones don't contribute very much. So I end up with 1. So this is just to show, for one, if what it means by it being inconclusive is that when it equals 1, you could have it diverging, you could have it converging. The other thing to note here is that for something like a p-series test, this isn't a very good, or a p-series, this isn't a very good test, because you're always going to get 1. What you're going to end up with is your leading coefficients. If they're n cubed, I would end up with n cubed over n cubed plus some smaller terms. This is always, for a p-series, this will always equal 1. It'll always be inconclusive. So we don't want to use it for those types. It's more when we have things like these, where I can, especially for things where I'm looking at factorials or things to the nth power, especially comparing them. Notice I was doing the same thing in both of these, because we can simplify these n plus first terms this way and get some cancellation and you get a resulting limit that's not hard to evaluate. This one was a little bit harder to evaluate, but again, this is one that's worth knowing. Okay, now let's take a look at the root test. So the root test actually looks surprisingly like the ratio test. All right. So if what we're doing is we're taking the nth root of the nth term of the series, but the conditions are the same. If the limit of the nth root of the nth term is less than 1, then it converges absolutely. If it's greater than 1, including infinity, it diverges, and if it equals 1, it's inconclusive. So I just want to show a couple examples of how to apply this test. So we have n equals 1 to infinity e to the 2n over n to the n. I want to point out, because we're taking the nth root, this test is particularly useful if I have things with a power of n in the terms. And we'll see why here. So limit as n goes to infinity, and we're going to have the nth root of the absolute value of e to the 2n over n to the n. Absolute value, unnecessary here. We don't have an alternating. So I'm going to just rewrite this. Limit as n goes to infinity, e to the 2n over n to the n to the 1 over n. And then we can rewrite this as e to the 2n to the 1 over n over n to the n to the 1 over n. Now we know when we have a power raised to a power, that's e to the 2n. we multiply the powers. All right, so we're going to multiply these powers, and I'm going to take the limit as n goes to infinity. Well, 2n times 1 over n is just going to leave me with 2. So my numerator is e squared. N times 1 over n is 1, so that's going to be e squared over n. E squared is a constant, right? So it's constant. This is growing without bound. This is going to equal 0, and so this shows that it converges. Okay, so that's, you can see where, taking the nth root of things that are raised to the nth power, you end up with some simplification, results in a limit that's easy to evaluate. Okay, let's take just a look at one more example here. I'm going to take a look at the sum, n equals 1 to infinity. I'm going to look at 2 to the n over n plus 1, again to the nth power. That nth power is kind of an indicator that the root test would be a useful test here. So let's take the limit as n goes to infinity of the nth root of 2n over n plus 1 to the nth power. This is going to be the limit as n goes to infinity of 2n over n plus 1 to the nth power to the 1 over n. Again, raising a power to a power, we multiply, and this basically cancel, or at least result in a power of 1. So I'm just left with 2n over n plus 1. Again, we look at the leading coefficients, the coefficients of the largest terms, and this is going to reduce to the ratio of 2 to the n over n, so that is going to equal 2, which is greater than 1, so this will diverge. What's interesting to note is if I were to just switch this around and look at the series n plus 1 over 2n to the n, right? I could repeat this whole thing, and the limit I would get at the end would be the inverse of this. So it would be 1/2, right? So everything else looks exactly the same, except I'm going to have n plus 1 over 2n here. So it will converge to 1/2, and therefore this one would converge by the root test. Okay, so those are two more tests that are fairly easy to apply. The big drawback with both of them is this inconclusive piece. You could end up with some that are inconclusive, but usually in that case, that means there's another test that's more useful. The thing to look for, as we said before, if I have things to the nth power or factorials, then the ratio test is a good one to use because of the cancellation we get. Here, for the root test, if we have things with an n in the power on both of them, then that's the root test is a good one to use.